professor at the University of Edinburgh. I'm also the co-chair of the SEOSAW steering committee. And I'm running the session about how to use SEOSAW data to estimate woody biomass and carbon stocks. And ahead of our coding session on Thursday, I thought it would be good to record a video which introduces the topic of biomass estimation so that you can read up on the science of it and can really focus on the coding when we meet on Thursday. So I've prepared a bit of a talk about how we do biomass estimation, linked very much to the kind of data that you collect in SEOSAW. So this is a picture of the carbon stocks from a dry Miombo woodland in central Mozambique. It's where I did my PhD. And the numbers inside each pool represent the size of the amount of carbon, the size of the carbon pool, and the uncertainty. And what you can see is that there's carbon in the stems, in the wood, about 21 tons of carbon per hectare. All these units are tons of carbon per hectare. And there's about 8.5 tons in the coarse roots. That's the big bits of roots, not the fine stuff. But there's carbon in other places in the ecosystem, as well as in the wood. The wood is maybe the one we're most used to thinking about, but there's carbon in the leaves, although not very much, less than a ton per hectare in this ecosystem. There's carbon in the grass and in the small trees and the saplings. But the big pool of carbon is actually in the soil. We're not going to talk any more about soil carbon, but I wanted to start off by showing you that there's at least 40 in the surface soil, 30 in the deeper soils tons of carbon per hectare. And that's actually a lot more than what's stored in the woody biomass. But a lot of what we do, we're actually interested in the woody biomass because that's a kind of store of carbon that people are interested in managing. It's relatively easy to get trees to grow. And like all wood, is 50% carbon, so you can quickly accumulate carbon in trees. It's much trickier, really, to do that in the soil. How do we come up with these numbers for the stem and the roots? Well, that's the topic for today. I'm not going to talk about the leaf carbon or the grass carbon any further. The small trees we might cover later if people are interested in. We've got some data we could do that with, but we won't do the soil carbon. That's kind of a different topic. So how do we come up with these numbers? Well, if you really want to know how much carbon is in your savanna or your woodland, the easiest thing to do is to dig up all the trees, all their roots, cut them down and weigh them all. And then you will know exactly how much biomass there is in your ecosystem. And as the last slide said, about half the dry biomass is carbon. So you would just chop them all down, like we're doing here, chop them up into little bits, put them on your scales and weigh them. And that can be great fun, but it's not the ideal way of measuring the biomass over large areas. It takes a lot of time. It's also very destructive. So people have developed alternatives to just chopping all the trees down and weighing them. And one of them, a high-tech one, is to use some kind of laser scanning. It could be from the ground, it could be from the air, to get the volume of all the trees. And then you go from volume to mass if you know the wood density. That's extremely complicated and high-tech. And it takes a lot of effort to get the laser scanners into the field. So we're not going to talk further about that. People try to do it with satellites, which is something my group works on a lot. But it's never a direct measurement of biomass. And actually you need lots of good measurements in the field to calibrate any of the remote sensing approaches that use satellite data. But they can be very effective for scaling up your estimates of biomass, but you still need good estimates in your plots to make that method work. So the approach that we're going to talk about is sometimes called biometry, like measuring the biology or the biological elements of the system, and then allometry, which is about the relationship between the size of one part of an organism and the other. And biometry in this case is what SEOSAW does, measuring all the plots. Measuring all the trees on the plot, and allometry is a kind of separate study that you might do to establish the relationship between diameter and biomass. And that's what we're actually doing in these pictures here in Mozambique, is building a local allometry. So what is an allometric occasion? Well, here's the introduction that nature provide, that link down there. Allometry in the broadest sense describes how one characteristic of a living creature changes with size. And it used to always refer to like how one part of the organism was related to the size of another part. So the palm of this crab to its shell width has a very nice relationship, and often allometric relationships are on a log scale, so look out for that. And often when you put them on a log scale, you get a straight line. This is an example of the size of an organ, so the size of the heart scales very strongly with the size of the body. The brain has a bit more of a complicated non-linear relationship in log-log space. But allometry can mean anything related, any size related to any other size of an organism. So when you say allometric equation, you need to say what kind of allometric equation you're talking about. And the one that we'll most commonly talk about is the relationship between diameter of a tree and its biomass. But there are lots of other allometric equations about trees. You can have the diameter to the crown width or to the height. So I'll sometimes call them a diameter biomass allometric or just a biomass allometric. Sometimes they're not to biomass, they're to volume, and then you go from volume to biomass. But nearly always, I think all the studies here is going to be about diameter and the relation of diameter to the woody biomass of a tree. And here's an example of one. So this is from Dowd's PhD and associated publication in forests. And it shows how the biomass of a tree, this is in kilos here, is related to its diameter. And you see this very characteristic shape of the curve. This is not a log scale or anything like that. And just with normal units, you see a kind of exponentially rising increase. So big trees have more biomass, but exponentially so. So really big trees have a lot of biomass in them. And this is your classic biomass allometry. So you can measure the diameter of a tree, and then you can look up using the equation that describes this line what the biomass is. And on the axis you can see this is Dowd's in the solid line, and then he's compared it to some other allometric equations that people published for the Miombo region. So how do you make one of those lines? How do you get an allometric equation like that? Well, this is the same study I showed you before. This is us working in Mozambique. Here you can see the trees have been chopped down, and they've been chopped up into little bits, and then they're being hung on the scales here to measure them. And that way you find the total mass of the tree. Now that's the wet mass. So you need to dry out some subsamples, which is what we're doing here in our solar ovens. And then you get the dry mass, and then you apply that conversion and you get the biomass of the tree. And then either you can assume that half of the biomass is carbon, or you can send it to a lab for that to be verified. And I think in this study it was 47% of the dry mass was carbon, and it's always very similar. But that's a lot of work and quite time consuming, and you have to be very selective about which trees you harvested and which species you choose. And in this study we only harvested 21 trees. It was so much work, but people have done much larger and much more thorough allometric equations since then. But you don't want to do this every time that you need to estimate the biomass. So people publish these allometric equations, and then other people can use them if they think they're relevant to the ecosystem that they're working in. So if you've got a good allometric equation, you can measure a lot of trees, but not the biomass. You can measure things that are really easy to measure. You can measure the diameter of the trees, you can measure the height, not quite so easy. Sometimes people measure the wood density, or sometimes they look it up. But even people measure other things that are related to the biomass. It could be the crown condition or the crown size as well. But I'm going to use these abbreviations throughout. So B for a tree or a stem is a little b means biomass, a little d means diameter, a little h means height, and rho means wood density. So you go and collect that data on lots of plots, lots of trees. You can spend a lot of time doing your inventory work. And then using the allometric equation of biomass, it's a function, that's what the F means there, of diameter, height, wood density, things like that. And you can look that bit up from the literature. And different allometric equations will ask for different things. Some will just be diameter, some will be diameter and height, some will include wood density. The most popular ones have a mixture of those three variables. And then once you apply your allometric equation for each stem, each B, you can add it up for all the trees on the plot. And then use a capital B for anything that's at plot level. So B is like tons of biomass per hectare. And then you can estimate an average from a collection of plots, and that's what we'll do on Thursday. And then C is the carbon stocks. So if your allometry was in B in terms of biomass, then you need to divide it by 2 or divide it by 0.47 to get it into carbon stocks. And if you want to read through the whole process of developing the allometric equation, doing the plots, combining the two to get an average of how much carbon is in the ecosystem, the paper from my PhD here has a worked example of doing all of that to come up with those numbers that you saw right at the beginning. So if you're unsure about this, if you haven't done biomass estimation before, I think having a quick skim of that paper will just give you a sense of the methods that we're going to use on Thursday. So in terms of SEOSAW, what does this mean? Well, we tried to make this easy, so you don't have to go and do this for every one of your plots that is in the SEOSAW database. However, it's important you know what we did to get to those biomass estimates for the plots, and that's kind of the point of this practical. So you know what's going on inside the SEOSAW database. So we'll look at some different allometric equations and think about which one you might want to use for different purposes. We'll apply the allometric equations to some real inventory data and see if it makes a difference if you choose different allometric equations. And we'll get on in the second part of the practical to seeing what comes out of the SEOSAW database and seeing if you can come up with the same numbers so you can be confident that you know what the SEOSAW database is doing. There's a nice sample of data. You've probably come across some of it already in other parts of the workshop, but we'll look at some real inventory data and some of the issues that come in when you have real data that has errors and uncertainties in it. So here's 2 different allometrics you could find in the literature. The first one is the one I mentioned from my work in central Mozambique. Each dot on here is a tree that we chopped down and weighed in the way I described, and this is in kilograms of carbon, and this is its diameter. And it has that same characteristic curve. Now, I was so inclined to dig up the roots with a lot of help, and so there's another line here, which is the root biomass. So we've got an equation that predicts the above ground biomass and an equation that predicts the root biomass. Grey is the above ground biomass, dotted line is the root, and the solid dark line is the total, the root and the stem added together. But the biggest tree we chopped down in that work was 73 centimeters, so it wasn't that big by the scale of things. So I put this example from Wilson Magasha's work, where he did the same thing with many more trees and many more sites across Tanzania. And if you look on the x-axis of these, especially in the Lindi region, they sampled some really big trees, and that's a lot more work. So those trees of over 100, 110 centimeters weigh more than a ton of biomass, so more than 500 kilos. 5 tons, so 5 tons of carbon, so 10 tons of biomass. And you can imagine the work involved in felling and weighing a 10-ton tree. You don't have to do that because Wilson did it for you. So these equations are what we call a local allometry because they're very specific to the sites where they were developed. And in Wilson's case, there's 4 sites across Tanzania. In my case, there's 1 site in central Mozambique. And what we don't really know is how far you can go from where these were developed to your study site and still be able to use these equations. But they're still very useful, but we call them local allometries, and there are lots to choose from. Like I say, the plus point of them is that they're very relevant because they're local. So if you're doing a study in central Mozambique, great, you use the top one. If you're doing a study in the Miombo of Tanzania, you should use Wilson's. But certainly in my case, they're made from only a few trees. And if that tree had been a bit of a funny shape and a lot bigger, the line would look different. If it had been broken that day, the day before, and the point was down there, this line would look different. And it's actually quite hard to generate a lot of data, particularly for these large trees. Like I say, they're 10 tons worth of tree here that we're dealing with, so no one wants to chop down lots of those. And so there's a lot of random error in local allometries with small sample sizes or without large trees. That hasn't stopped us as a scientific community from building lots of allometric relationships. So as part of the SECO project, we tried to find all the allometric relationships we could for the dry tropics. And we found hundreds. People have made these all over the planet in all these different ecosystems. So in the African arid savannas, which is this box, you can see we found a whole load of different equations listed there. In African wet savannas, there's not so many. In the Miombo, people have really loved doing this, so there's lots to choose from. But that's true also in the Cerrado and in other regions of the dry tropics. So there's lots of local allometries to choose from, so you can nearly always find one that's relevant to your ecosystem. The difficulty is knowing which one to use often. If I zoom in, you can see that this is just for the Miombo. There's all these different ones, and they all give slightly different answers. So you start to think, yeah, how do I know which one is the most appropriate? So this is diameter again and biomass on this scale. And they're all different, and it's true that if you go different places, the relationship between diameter and biomass changes. So you'd expect them all to be different, but it can make it hard to choose. So how do you know which to use? Well, one approach is not to use the local ones, and instead to use what we call a global allometry. And the kind of centerpiece of this work in the literature still is a piece of work by Jérôme Chave that was done in 2015, where he assembled lots and lots of allometric data from across the world, including many of the data sets I've shown you that were used for the local allometries. Right, so you'll see some of the same authors. So like there's Wilson again on this because he put in the data from his local allometry, and I put in the data from my Mozambican one. And that gives us a much bigger data set to play with. So here's diameter against biomass again. It's a slightly different shape of a line, but you can see that the advantage is it goes up to really big tree sizes, 200, so 60-ton trees almost. I think up there it's even larger, getting on for 70. And now we've got loads of data down at sort of 70, 80, 90, 100, where we were relying on very few data points before. So that's the plus side of having a global allometry, is you get a huge data set, and you can average away some of the kind of random errors that you might get. But of course, if you look at that map, you might think, what have the trees that came from these sites got to do with my site in Kenya or wherever you're working? And that's the problem. You've got lots of big trees, but you don't know how relevant they are to the system that you're studying. However, Jérôme made two bits of progress in this that get over that issue somewhat. So, the good models from that equation often need wood density and height. And Jérôme was able to show that you really do need an estimate of wood density, and you really do need an estimate of height, as well as diameter, to get a good estimate of biomass. And if you think that means you have to measure height everywhere you go, you're only half right, but you're right to worry that that might be a lot of work. Because what was nice was that this big data set, we were able to show that there's a relationship between height and diameter. And that varies across the tropics in a quite predictable way. If you go to hot places, trees get shorter and fatter for the same diameter. So they're kind of stumpy like this. And if you go to wetter places, they are taller and skinnier, right? So actually, by knowing something about the climate, we can predict what the height would be from the diameter. And that helps us transpose this equation and use it in different places, even though we know that the allometry changes from place to place. So the Chave et al. 2014 allometry is very widely used. It's got thousands and thousands of citations because it's become almost the standard way to estimate biomass if you don't have a good local allometry from a site nearby. And so it's very widely used, and partly it's very widely used because it's been implemented in this really good biomass package. This is an R package that we're going to be using. It makes it really easy to use it, and use it in quite sophisticated ways. So that's what we're going to do for the workshop on Thursday to start with. It gives you some control over what you do, so we're going to try and understand the options that the biomass package gives you. But put simply, all you have to do is type the name of the function, which is compute AGB, tell it the diameter of the tree, tell it the wood density, and those two are required. And then, if you can, tell it the height. If you tell it the height, you don't need this coordinate argument. But if you tell it the height, it will come back and it will give you an estimate of the biomass of your tree, just using the equation that I showed you on the previous slide. However, if you haven't measured the height, it uses that height-diameter relationship to estimate what the height is and then puts it into the same equation. But to do that, it needs to know where you are because it needs to look up something about the climate. So you can provide it with height, or you can provide it with your latitude and longitude. And if you give it those 3 ingredients, it will estimate the biomass for you. Very simple. But actually, it's not that simple. There are issues with all of the different components of what you need to enter. So I'm going to go through one by one. First of all, look at the diameter, then look at the wood density data, and then look at the height data. And we're going to think a bit about how complicated it can or cannot be to get good data to feed into this equation. So the most common issue, I think, in the SEOSAW data is that all of these allometric equations are designed for diameters measured at 1.3, so breast height. But very often, it doesn't make sense to measure your trees at 1.3, and that can be because you're in an ecosystem where they are branching by that point, and it's much better to kneel down to the tree and measure it at 0.3, which is what the SEOSAW protocol says to do if 1.3 isn't appropriate, or because weird things have happened to your tree. So it's not uncommon to see all kinds of deformities and things like that at the height that you're meant to be measuring, and so you have to move the point of measurement to a different height. So how do you deal with that? Well, you need some way of converting to what the height would have been at 1.3 to be able to use any of these allometrics. So don't just feed data from measurements at 0.3 into the SHAV allometry or any other allometry if it says it was based on 1.3. But as long as you account for that, there are a few other snafus, but there's not too many issues. So sometimes people measure circumference to check you haven't had circumference recorded. We still see the classic issues about getting the units right. And then I think probably the most common thing that gives you the biggest error is losing a decimal point. So in allometry, that really matters because the difference between a 5 centimeter tree and a 50 centimeter tree is enormous. And I think you did that in the cleaning workshop last week. So always record a decimal point and always write a 0 after the decimal point, just to help avoid those kind of errors. So diameter data, mostly quite straightforward, but you might have to do the conversion. And for people who are interested in the conversion from 0.3 to 1.3, I will talk about that in the class on Thursday. Then you need wood density data. And that can be hard to measure. You get a core out and you have to go and do lots of lab work to accurately measure the wood density of a tree. So instead, we define it as a taxonomic problem. We say if you know the species of the tree, then you can look up the wood density because most trees of a given species have very similar wood density. And the biomass package makes it even easier because it has a built-in database of wood density measurements that it queries. So that get wood density function, if you pass it the name of your tree, the genus and the species, if you can, the family or constraint to which region you're working in, it will return an estimate from that database with the wood density data in. So as long as you know the species, you can look up the wood density. And that's why I say wood density is a taxonomic problem, because you do have to have good species IDs. And then you have to hope that there's some wood density data for your species in the database. If there's not, that argument there, add wood density database, you can use that to add more data to the database. It doesn't make it public, but in your calculations. And that will give you much better estimates if you're working with species for which there's not much data. And that is very important in the SEOSAW region, actually, to add some extra wood density data, because the database isn't super good for a lot of the SEOSAW region. So some common issues if you're looking at wood density is you spell the genus or the species wrong, and even 1 or 2 letters wrong can throw the whole thing off. The database also has different taxonomy. We'll come to that in a second. You might be using a different name for the same species. But a more fundamental problem is that the database doesn't have a huge amount of data from the dry tropics, so you might be working with species that there's no data for. And the default for region is world. So if there's a tree of a similar genus, but from a different continent, it will use wood density data for that genus, even if it's a completely different type of tree. So you can change region and look up wood density data only using the data from a particular continent or even subpart of a continent. And I recommend you mostly do that. Don't use the default of world. But I thought it would be interesting to look at how much wood density data is in the biomass package for species we really care about. So this table shows you some common species, and these are actually the most common species in the SEOSAW database. So this is the genus and the specific name. N is the number of stems in the SEOSAW database of that species. So you can see some very popular trees at the top. You can see the miombo coming in and the mapani at the bottom, 18,000 of those. But then if you look across here, number of individuals, this is how many measurements of wood density are in the database. And you can ignore 951 because that's our undetermined species. There's only 2 for Diploronicus condylocarpon, even though that's our most popular species that we've measured in the SEOSAW database. There's only 2 wood density measurements in there, which give 0.6 and have this quite small standard deviation. Even for very famous species like Brachystegia spikiformis, there's only 4 measurements of wood density in the database. So if you think maybe it varies a bit from place to place, you might want a few more than 4 measurements. Same for Julbernardia, there's only 5. And in fact, that's not even specific to paniculata. If you see here it says level, that means that it's had to match Julbernardia paniculata at genus level. So that could include some of the other Julbernardias, which I think might include trees from quite different environments. So there's not a lot of wood density data in the biomass packages database. And it has some tricks to get around that, but you shouldn't forget that. And you should try, if you can, to add some more wood density data if you have any available. This is just a quick summary of the species in the SEOSAW database, which is about 12,000. There is species level data for 320 of them. So there is some wood density data for 320 of our species, but there's only genus level data for 630. And then there's 300 for which there's no match at all. So it isn't a perfect wood density database, and it does introduce some extra uncertainties having to provide wood density to the biomass estimation. And that's another reason why using a local allometry can be better, because it doesn't rely on a wood density database that might be quite incomplete. If you're interested in that problem, we've got a big effort underway in SEOSAW to collect more wood density data. So if you have some and you feel like sharing it and contributing to a regional analysis of wood density, then please do get in touch. Now, the taxonomic problem can become a really taxing problem if you're not careful with your names. So if you put into the biomass package, biomass get wood density, that's the name of the function, and you write acacia nigrescens, which you might do, you get back some wood density data. So the family, the genus, the species, the mean wood density, 0.78, 0.79, standard deviation, about 0.1. It's matched it only at genus level though, but you get 115 of them, right? So that's basically of all the acacias in the wood density database, there's 115 of them, and that's their wood density. So it's not great because it hasn't been able to match to your species, but at least you've got a lot of data in there. Now, say you've moved with the times and you don't call it acacia anymore, you call it Senegalia. So you use the same function, you type that into R, and you put Senegalia nigrescens in. It says, there is no exact match for the family, genus, or the species. You need to provide your own data. And that's because they haven't updated the underlying taxonomy in the biomass package to use Senegalia, they just use acacia still. And you might think, when are they ever going to get with the program? But whatever their taxonomic backbone is, hasn't been updated to record this split in the acacias. So you do have to be a bit careful what's going on. You can't just blindly put your species name in, because putting in what you might think of as the right species name is not going to give you any wood density data back for the Senegalias. The third bit you need to put in is height. Height is pretty easy, and I think most people can measure height very accurately if they take the time and if they can see the top of the tree. And most of the time, you don't have a lot of time and you can't see the top of the tree. So the main issues are actually that you didn't measure height, or you took ages and ages measuring height very carefully, and that meant you couldn't do lots of plots. So it's a bit of a, I don't know, like a debated topic, whether you should measure a lot of height. You should take a lot of height measurements. It's a real trade-off. The SEOSAW manual goes into it in great detail. But for now, what I'll say is if you don't have height measurements, you can use a height diameter allometry to estimate it, and that's fine for our purposes today. If you don't have height, remember in the equation, it wanted your coordinates, and they have to be in the order long and then lat, which is a bit funny. You might be used to thinking about latitude and longitude, but the argument here is you do the x coordinate, and then you do the y coordinate, so long and then lat. So here's an example of the site in Mozambique. If you're doing it with a data frame, you need to paste in the 2 columns. You use cbind, not C, so that often catches people. It only takes decimal degrees, and yeah, if you don't have the locations, it doesn't actually matter that much. You can look them up roughly for where you're working, because it's all based on climate data. So the climate data isn't very high resolution anyway. So you could go in and look roughly where your plot is and get the coordinates that way. So if you have all of those things, then you can use the Sharp equations and you can get pretty good biomass estimates out of the biomass package. I just thought I'd come back to local versus global. We'll talk about that a bit more in the class, but the Sharp equation is really good if you don't have a good local allometry. It's a great thing to use. In that situation, it's a bit harder to know what to do if there's a really good local allometry nearby. How would you know which was better? And I'd say there's some evidence that if the local allometry didn't have a lot of big trees in it, then you might be better off using the Sharp one anyway. So I would certainly be quite comfortable using the Sharp one at my site, where we only put 21 trees into the allometry. If I'd done hundreds of trees, I might think it's probably better to use the local one. But that's just a judgment issue, really. There's a few extra things we could talk about, but they're mostly for the practical. So we'll do the conversions from 0.3 to 1.3, for example, or from any height actually that you measured the diameter, the point of measurement of the diameter. We'll cover that, but you just need to develop another equation to scale from wherever you did measure the tree to 1.3. You might want to think about how accurate the biomass estimate is, and there's a lot of different ways to do that. We'll do one of them in the practical by comparing the estimates from different allometries. If you're considering making your own one for a sort of understudied ecosystem or ecoregion, I think there's a couple of sort of new papers out where you can look and think about whether it's worth doing that and how best to do it to add to the existing knowledge. That's quite an interesting topic. And then, that Sharp data is pan-tropical, it's not dry tropical. So you might think, could we make our own one for the dry tropics? And that's a kind of current hot topic, I would say. It's something we're working on in the SEOSAW and SECO projects to make some that are specific to the dry tropics. Whether we can get enough good quality destructive harvest data like Sharp did for the whole of the tropics, I don't know. But you can see the temptation to make one that's kind of doesn't use all of those wet tropic trees as well. And then I didn't talk about root biomass, but it basically works exactly the same way. You can find equations that predict the root biomass. In fact, I think all of the ones I cite here do that. So you can use the equations there. Just look in those papers, and they have exactly the same type of equation applied for root biomass. But there isn't a global one like the Sharp paper for root biomass. We need to talk about biomass change at some point in all of this, but I think we'll probably do that at the workshop in Kenya rather than in the prep work, because that's a whole nother story. So here are the 4 papers. I think if you can skim read all of these, that would really help. If you have trouble getting hold of them, then please talk to me. But the top one, the Sharp one, we're going to use a lot, so it'd be good if you know where the equations that we're going to use come from, and then 3 are these local ones, just to give you the kind of contrasting approach of using local allometries. And that's it. If anything was unclear, please let me know. I'm always looking to improve these kind of videos, but otherwise looking forward to seeing you all on Thursday for the practical. Bye.